Now for the last segment in our introduction to the solar system. And this is about exoplanets. If our solar system formed and we have planets around our star and the model of how that happened is correct, then there are going to be planets around other stars. In fact, it was in 1992 that the Université de Genève announced the first discovery of an exoplanet. This is a planet that they found using what we now would will call, or what is called, the transit method. What they did was they observed the fact that this star would dim, and it was dimming because the planet was passing in front of us. So we'll get into exoplanets and different ways of discovering them. Um, but for now, this question. You should know the answer to this after we talked about Doppler shifting for the last exam. What will have the most noticeable Doppler shift? Something that's moving fast? Something that's moving slow? Something moving away from us? Or something moving towards us? I think all of you should know the answer to this one at this point, right? The faster something is moving, the more it Doppler shifts. Just like the faster an ambulance is coming down the road, the more it Doppler shifts. The same is true of light. This is one of the techniques we use for discovering planets. How does this help? Well, you've got a star, and you've got some unseen planet out there going around it, right? And that planet is going to cause the star to wobble back and forth. In fact, like the Earth wobbles in its orbit with the moon, the sun is going to wobble back and forth a little bit, and that means, right, that when it's wobbling towards us, it's blue shifted a little bit. When it's wobbling away from us, it's red shifted a little bit. And we can measure these shifts and turn that into a velocity. So here we've got a plot of the velocity of a star with respect to us over time, and you can see it's wobbling back and forth. And this wobble back and forth indicates that there is a planet orbiting it, causing it to wobble. Which planets move the fastest? Planets close to the star, planets far from the star, large planets, small planets. Now, you might be misled to say, oh, well, it's going to be small planets because that's true in our solar system. But that's only because the small planets in our solar system are where? Close to the star. Planets close to the star orbit faster, move faster. This is just Kepler's law, right? P squared equals A cubed. So the closer you are to the star, the faster the planet is going to have to go around it. So as I mentioned earlier, the Université de Genève, the reason they discovered, or the method they used for discovering a planet around another star, was to watch the brightness of the star over a long period of time. They were using an older telescope, and for a while we only used older telescopes to find exoplanets because it's only with an older telescope that you could afford to look at the same star again and again and again and again over a long period of time. So they did this in Geneva, and they found this exoplanet because it caused a little dip in the brightness of the star. Every time it went in front of it, the brightness of the star dipped. So they found an exoplanet that way. Also, when we do this, if we start looking at the spectra carefully, we can see an impact of the atmosphere of this planet on the spectra coming from the star because it will absorb some of that light in a way that other than just being in the way, right? Here's an example here. This is the spectra from a star. Normally it wouldn't go down this far, but when the planet is going across the star, it gets this extra bit, this excess absorption due to the atmosphere of the planet. Really cool way of finding exoplanets is to actually take a picture of them. Now this is hard to do because they are very close, relatively speaking, to their stars, and it's something that only works in the infrared. And you can see here a picture of an exoplanet around a star, and you can see it's quite far out, 55 AU. So it's almost twice as far from its sun or its star as Neptune is from our sun. And here you get to in the infrared, and one of the reasons you have to go out in the infrared is why? Well, planets aren't big, bright, hot objects like stars, right? And so, where's their temperature in black body radiation, in their black body spectrum, where are they going to peak? They're going to peak off in the infrared. So, if you want to see planets, you're going to have to look in the infrared. Here is another here's a star, um, and you can see the star has done a decent job of clearing out some of the stuff around it, and well, and this is also part of the filtering to see the planetary, the disk, the proto disk around it. Um, and here in this little bitty block, you can see between 2004 and 2006, this mass right here moved from here to here, right? So this is a planet forming, and it's going to slowly accrete more and more material out of this disk. Number of exoplanets discovered per year has risen dramatically over the years. Um, a lot of this is because we have, in fact, built telescopes specifically to search for exoplanets. And so these telescopes are doing a great job of finding exoplanets. And you can see where the data from these begins to come in. And man, we get a lot of exoplanets out of that study. All right, and most of these, this green, that's from transits. Radial velocity is the red. So a lot of ways to get at this, but most of them right now are either radial velocity or transits. This is a map, not a map, this is a diagram of orbital period in days versus the size relative to Earth's radius, the size of planets. All right, and so the blue dots are all as of January 25th. The orange dot, the yellow dots are July 2015, and so you can see a good number were added in that period of time. Now here's Earth, right? Earth, relative to the Earth size, Earth is exactly the same size as the Earth, and you come down here, 365 days. All right, there's 100, 200, 300, 365 days. So Earth is right in here. Right? Neptune 4 times as big, Jupiter 10 times as big, and you can see a lot of exoplanets. There are a good number of exoplanets that are big, but then there's this vast number in here that we're finding that are comparable to us and or Neptune. Where do we look for this? Well, you look out into these vast nebula out in space, and you can begin to see places where there are stars that have formed, and they are beginning to gather the gas together. And so out in here is where you begin to see all this formation of exoplanets. Here's a great image of a proto-sun here in the middle, and you can see where exoplanets are beginning to form and they're beginning to sweep out their area. And so the planets that are forming in this will slowly gather in all this gas that's in the planetary or the solar disk right now. It'll slowly gather in all this gas until we're down to a sun and the planets going around. All right, that's it for the introduction to the solar system, and I will see you in class soon.